All right, hey everyone. Today we're going to be going over AVL trees and some hashing. So this material was from section 4, which was also the midterm review section. So we didn't get to go through like that much about AVL trees and hashing, but I just wanted to give sort of a brief introduction to them. And then if you want some more videos on AVL trees, check out the other videos in this playlist. And some of the other TAs have covered more in-depth AVL tree problems. That you can find there. Cool. So let's get started. An AVL tree. So we introduced this concept of like an AVL tree, which was sort of like an improved version of a binary search tree. So if you remember a binary search tree, this is an example here. A binary search tree, it's a tree with every node having two children. Those children can be null. You can see the 7 node has like a null child for its left and a non-null child for its right. Every node has 2 children, which makes it binary. And then it's a search tree, which means that from any node, we have this invariant that all nodes to the left contain a smaller value than a given node, and all nodes to the right contain a larger value than a given node. So you can see this 10, everything to the left is less than it, and everything to the right is greater than it. And this property holds for every single one of these nodes. You can go through and take a look at that. But we do have a problem with just a normal BST, and this has kind of motivated the concept for an AVL tree. So a BST, right, the only invariant that we have is just that all nodes to the left are less than a node, and all nodes to the right are greater than a node. But it doesn't say anything about like the balance of the structure. So you can think of like this, for example. These sequences of inserts result in this BST. And this is a valid BST. It satisfies our BST invariant. But if we did any operations on this, like we kind of introduced the idea that like, when you have a tree, you get this like nice logarithmic runtime because, as the levels grow, like the height of the tree is like logarithmic with respect to like the number of nodes in the tree, usually, unless you have like a really bad case like this. So we can get this like worst case behavior. Which kind of motivated like maybe you want like to avoid this worst case behavior basically, because if you ask any question about like a BST, like what's the worst case runtime of X in a BST, you'll always want to be thinking about like this type of structure because BST can be this type of structure. So you actually get like pretty bad runtimes for a few like pretty bad worst case runtimes, which is where this AVL tree comes in. And for an AVL tree, it's just a BST, but it's balanced. So what that means is, we'll kind of define like the concept of balanced. What it means for this class is that the difference in heights between the 2 subtrees of any node is no greater than 1. Kind of a mouthful, but what you can sort of think of as balanced is like this. If you had 3 nodes, this is balanced, right? Because like everything's like there's no like worst case behavior here. We can go back to this definition though. When the difference in height between the subtrees is no greater than 1. I looked at this 8, and I was wondering, okay, what's the height of its left subtree? That's going to be 1. What's the height of its right subtree? That's going to be 1 as well. So the difference in height between these subtrees is no greater than 1, right? Because the difference is 0. By the way, just recalling, like the way that we calculate height is by just counting the number of these like arrows here. Is kind of how you can think of that. So if we go over here and we look at this tree and we're wondering, is this balanced? Well, the height of its left subtree starting at 10, the height of that left subtree is 0, right? There's no nodes there. There's no arrows. The height of its right subtree is 1, 2. So we can think about, like, does this satisfy the property that the difference in height between the subtrees is no greater than 1? Well, the height of the left subtree is 0. The height of the right subtree is 2. So the height difference is greater than 1. So this is not balanced. But similarly, we have these 2 structures are balanced, right? So, even though there is a difference of 1 in the height of the subtrees with this 8 here, we still consider that balanced. And we also consider this balanced, like, 0 and 0, that's also balanced. And the big point about being balanced is a balanced tree with like n items has a height of O of log n. That's in comparison to like this over here, where a BST, if it's not balanced, the height is going to be O of n for n elements in this worst case. But if it's balanced, it's guaranteed to be log n. yeah, so like I kind of said, the solution is AVL trees. The way that these work at a high level is that every time you insert a node, you basically reorder the tree if needed to put that node in and keep the balance property. So in this case, and we'll talk more about rotations. There's another video actually on rotations in this review videos playlist. So check that out if you're interested in it. I won't go too in depth into the rotations, but what you can think of is like if you had a tree that was just 3, 2, let's say, and then you inserted this 1 here. Now you look at this tree and you say, okay, well now this is unbalanced because there's a, at this node 3, the right subtree is height 0, the left subtree is height 2. So there's an imbalance. So what you're going to do is you're going to promote 2 to be like the root and move the 1 and the 3 to be the children of that 2. And then that becomes balanced. Again, there's another video on the AVL rotations, so check that out if you're interested. But the big idea is that this happens every time you insert a node into the tree. You have to check if you need to rebalance it. But like the invariant is basically that like every time you insert, the tree beforehand is already balanced. So the amount of nodes that you need to swap is actually like just a constant factor when you insert one node, because you can kind of assume that it's balanced beforehand. And then you insert one node and then you have to rebalance it there. But it's only adds like a constant runtime basically to do this rebalancing. But check out that other video if you're interested in watching the rebalancing stuff. Yeah, so we're going to go through a couple of questions here, and we're going to ask like, okay, for these structures, is this a valid BST and is this a valid AVL tree? So kind of remember the difference between the BST and the AVL tree. The AVL tree is just a BST that's balanced, right? So you always want to start off by saying like, first of all, is our structure a BST, and then is our structure an AVL tree? So if we looked at this first problem, this is not a valid BST, and this is because if we looked at the 7, remember our BST invariant says that every node to the right of 7 must be greater than it. So this 2 is in the right subtree of 7, but it's less than 7, right? So this is not a valid BST. And in this case, it's not a valid AVL tree as well, right? It must be a BST to be an AVL tree. An AVL tree is like a stricter version of a BST, is like the way to think about it. So this is not a valid AVL tree. So if we're looking at this one, the first thing that we would check is this a valid BST? Again, I'd give some more time for everyone to work this out on their own. Feel free to pause the video if you want to think about it on your own, but I'll just go through these for now. This is a valid BST. If we looked at any node, all of the nodes in its left subtree are less than it, and all of the nodes in its right subtree are greater than it. For every node, this holds true. You can go through and check that out. Is this a valid AVL tree, though? The answer here is no. So what we can do is look at some nodes and we can try to check their heights, right? So there's actually a few different nodes that work for this, but one example is this 42, right? The height of its left subtree is 1, 2, right? There's 2 arrows. The height of its right subtree is 0. So that violates our balance condition, right? Our balance condition said that there's no greater than 1 distance between our left and right subtrees. So this violates that. Again, this tree we would go through, is it a valid BST? It is, satisfies that BST property. And now we can kind of think, is this tree balanced? Can I find any node where the difference in height in its subtrees is more than 1? And no, this tree is also balanced. And notice, like, it doesn't have to be like perfectly balanced. Like, there are more, this 7's right subtree is a little bit higher than its left subtree, but it's only higher by 1. Right, and that's what really counts for this balance property. So this is just a quick introduction to AVL trees. Again, I think we have 2 more videos on this in this playlist, so definitely check those out if you're interested. We'll go more in depth there. Cool. The next thing that I wanted to cover really quickly was just a hashing intro. So by this point, I think you all have done the max assignment, so the hashing stuff. You should have it down basically, but if you want a refresher, here's an intro to hashing. Yeah, it might be helpful to study later on for your midterm or your other midterm or your final, something like that. So yeah, oh yeah, we also reference Project 2 in here. So yeah, so a hash table, just a quick introduction to it, is basically this structure that allows for constant time lookup and like insertion to this data structure. We really want this like constant time behavior. So for example, and also it's an implementation of like a dictionary, what we call. And a dictionary basically it's like a way of associating like a key and a value. Um, so you can, this is maybe not the best example, we'll get into one here, but basically a hash table that has, keys and values, and, each key is associated with one value, and you can look up a key, like say like, oh, what's the value associated with like any given key in about constant time, like our goal for a hash table. So what basically happens is you can kind of like see this example here. If I put at the key 0 the value foo, the way that it knows like where to put, like the keys can be any data type. So in this case they're integers, so it's maybe easier to convert to an index. But basically what's going to happen is you have this thing called a hash function that takes in a key. This key is x here. And basically what it does is a hash function takes in a key and it returns an index, or it returns a number basically. And you use that number to figure out like where in my table am I going to put this. In this case, it looks like the hash function is just x here. So like, if I hashed 0, I'm going to get 0 out. So basically what you do is you take that number from the hash table, which is like the 0. You mod it by your table size, because this number could be anything. It could be like 2 million. You mod it by your table size to get a number within your table index, and that gives me 0. And then what you do is you put the value foo at the bucket 0. So you say like, okay, so 0 foo is like in our hash table now. And the way that we get this constant time behavior is that now if I said like, hey, is 0 in my hash table? Instead of having to look through every index, right? I don't have to loop through every index and look for this. What I can do is I can say like, okay, if I'm interested, is 0 in my hash table? What I'm going to do is just hash 0, right? Go put it through that hash function, which is usually a constant time. Usually it's fast. And that gives me an index. And either foo is at that index or it's not. And that's how you get this constant time behavior, is that you basically only have to look at one like bucket is what we call it. You don't have to look at any other part of the data structure because the hash function tells you exactly where to look. Yeah, that's the main idea, and that's how we get this constant time behavior. Okay, one thing though that we have to be careful about is, if we looked over in this hash table here, for example, we only had 10 buckets here, right? I've got bucket 0 through bucket 9. Only 10 buckets, but you might want to insert more data, or maybe you want to like if I put at 10, if I did like 10 mod 10, that's also going to be 0. You can get these like collisions basically where like, multiple values are going to go to a single bucket basically. You can never avoid this basically. So we have to have some way of like saying like, okay, what if there's 2 things that are going to be at bucket 0? How do I resolve that? And one approach, which is the same approach that was used in the project, is to basically have a linked list at each bucket that keeps track of like everything that hashed there. So this is an example hash table where we get like, a really big table size. You'd never have a table size this big. But you can see here that like, for some reason, all 3 of these values, potato, rotato, and tato, yeah, we should have picked like better or easier things to say for this example. But all 3 of these vegetables or something, I don't know what these are, but all 3 of these things hash the same bucket. And so now what you would do is like, if you wanted to know like, okay, is potato in my hash table, the first thing that you would do is hash this string, and it would give you an index. Then you would check that index, and now there is a linked list here, so you're gonna have to look through like 3 values. But if you pick a good hash function, your data will be like relatively spread out. So yeah, you might have to look through like 3 different things to find it, but like that's hopefully constant time if you pick a good hash function, right? Because maybe there's only like 2 or 3 elements in there. There's hopefully not n elements in that one bucket, but there could be if you picked a bad hash function. And then we already talked about how to use this mod basically to wrap around for the table size. Basically, what happens is like a hash function can give you an arbitrarily large integer, basically. So like you could get like this integer from your hash function. But if you had a table size of 10, you can't say like, oh, put at the 5 trillionth index, put the potato here. So what you need to do is you need to mod by your table size. So you would take this number, and I would mod it by 10, and that actually just gives me 1, right? Because, yeah, like I'm just modding it by 10, and basically anytime I mod any number by 10, it's going to give me a value between 0 and 9. So you're guaranteed, oops, sorry. Where did I go? You're guaranteed to get like in your table with this. Cool. Yeah, and then also you want a hash function that evenly distributes the keys. We kind of talked about this a little bit earlier. Cool. Let's go through a problem. This problem's 2D on the section 4 handout. And we're going to go through just a couple of these calls here and kind of walk through like, okay, now that we saw that stuff about the hash table, how does this actually work? So basically here, suppose we have a hash table that uses separate chaining and has an internal capacity of 12. That separate chaining thing means that at every bucket, there's a linked list. And assume that each bucket is a linked list, where new elements are added to the front of that list. And we want to insert the following elements in the exact order using this hash function for x. So basically what we do is we're just going to go element by element. So first we're going to insert 0, then we're going to insert 4, then 7, then 1, then 2, etc., etc. Let's insert 0. Okay, the first thing that we do is hash this value. The hash function was 4x if given any input, right? So the first thing that I'm going to do is do 0 times 4, right? Because we had to put this through our hash function. So if I gave this hash function h of 0, I should get 4 times 0, which again is just 0. Okay, now that we have that number, we have to mod by our array length. Our array length is 12. So 0 mod 12, it's just 0. So we insert this item at index 0 here. Let's go on. Input of 4. This is maybe a little bit more interesting. The first thing that we do is put it through our hash function, right? So we have to do h of 4. H of 4 is going to give us 4 times 4. It's going to be 16. Then what you're going to do is take 16, mod it by the array length, and 16 mod 4. That's kind of like 16 mod 12. This is 16 like divided by 12. It's like, what's the remainder after dividing 16 by 12? The remainder would be 4, right? Because 12 goes into 16 once evenly with 4 remainder. We put this at index 4. And we're going to just keep repeating this process. Always just take the input, put it through the hash function, then mod it by the table length, then insert it, basically. So we get 7. 7 times 4 is 28. 28 mod 12 is 4, right? Because 12 goes into 28 twice to get 24, and then you have 4 left over. So then we insert this item at index 4. But there was already something in index 4, right? So now we're going to add to that linked list here, right? All of these buckets have linked lists, and we're going to add a 7 to the front of this linked list, like so. We get to 1. We see the same behavior. We're hashing to index 4. So unfortunately, take a look at this, right? We have a really big hash table, right? There's 12 values, but unfortunately, 3 things are hashing to the same bucket, and sometimes this just happens. It's hard to avoid. But we get the 1. We're going to go through that process again. The 2 goes at 8 for these reasons. The 3 goes at 0, etc., etc. I'll kind of click through these. Yeah, and then we get this as like our solution, basically. One way that might make it easier for you to do these problems is like you can take each of the keys that you want to insert, and basically you saw that what we did basically was that we first hashed it, right? So take that key, put it through the hash function, which was 4x, right? So 7 times 4 is 28, 1 times 4 is 4, 2 times 4 is 8, and then take that hash and then convert it to an index, right? So 0 mod 12 is 0. 16 mod 12 is 4. 28 mod 12 is 4. 4 mod 12 is 4, etc., etc. So you can do this first if you want, and then now you just know, okay, well then I'm putting 0 at index 0. I'm putting 4 at index 4. Putting 7 at index 4. 1 at index 4. It might help to kind of make this table as well. But this is our final result that we get. Yeah, and that's kind of the basics of hashing. Yeah. If you have any questions, feel free to post on the discussion board as a follow-up, and we'd be happy to answer them. All right. Thanks, everyone.